Right, and go. Okay, and so we'll talk about the Dirac delta function, and in order to do so, we'll talk about the field of a point charge at the origin, which has E equals Q over 4 pi epsilon naught r squared times r hat. And in the homework, you can have found the divergence of that in Cartesian coordinates, but now that we know about spherical coordinates, then you should use spherical coordinates to do this, really. The divergence of E will just be 1 over r squared times the partial with respect to r of r squared times the radial component of the electric field. There only is a radial component in this case. There's no theta and phi components because it's sticking radially outwards away from the origin. And so what we're finding then will be Q over 4 pi epsilon naught, which comes out as a constant, times 1 over r squared times the partial with respect to r of r squared times 1 over r squared, or in other words, the partial with respect to r of 1. So in other words, it immediately drops out that divergence is 0 in spherical coordinates. So as I said last time, got you to do it in Cartesian coordinates, in which case it is a lot more lengthy calculation. But then this just goes to show, yes, the expression for the divergence is, for example, more complicated in spherical coordinates than it is in Cartesian coordinates. But in a problem with spherical symmetry, typically it still ends up being easier to find the divergence in spherical coordinates than it would be to do the same thing in Cartesian coordinates, although of course either one will work. Now, in that homework problem, it says that this might be confusing, and why is this confusing? And the answer I was looking for was that this electric field has a net outwards flux for any surface that you're going to draw around the origin. I mean, clearly, if here is a charge sitting at the origin and I draw a sphere around that charge, then the electric field is everywhere outwards on the surface of that sphere. And so if this is radius r here, then say at this location right here, here's r hat, which is equal to n hat, the outwards normal. Everywhere on the surface of the sphere, r hat is equal to n hat. And so if we find E dot dA for any little piece of the sphere, then we'll find that that's Q over 4 pi epsilon naught r squared r hat dot dA times r hat, because the normal vector n hat is r hat, and so n hat dA is r hat times dA. So r hat dot r hat is 1, and so we just get Q over 4 pi epsilon naught r squared times dA for every point on the surface. And so therefore, the flux through that surface, the integral over the closed surface of E dot dA, is equal to just Q over 4 pi epsilon naught r squared times the integral of dA over the entire surface. But if I add up dA for the entire surface, that is the area of the surface, and so you just get Q over 4 pi epsilon naught r squared times 4 pi r squared, the area of the surface. R squareds cancel, so you just get Q, and 4 pi is 2 for that matter. So you just get Q over epsilon naught. So there is an outwards flux through that surface. Notice that it's independent of the radius of the surface, and soon enough we'll show that it also is independent of the shape of the surface as well by considering an arbitrary shaped surface and showing that you can map HP to that piece of that arbitrary shaped surface one by one onto the pieces of the little sphere surrounding the center. So what's weird about that? There's a flux through the surface. The divergence is 0 inside that surface, so why is it weird? What does that seem to contradict? There's a flux through this surface, Q over epsilon naught. The divergence is 0 inside that surface. What sort of beast that we met does that seem to be contradicting? Yes? What sort of mathematical theorem might we have talked about that seems to be incompatible with this notion that the divergence is 0 everywhere inside the surface, and yet there is a flux through the surface. What is this, an audience or an oil painting? The divergence theorem, yes, as a matter of fact, the divergence theorem. Because why are you looking at me like I'm crazy?
You ever said that before?
Yes, I've talked about the divergence theorem.
No, the oil painting.
Some people were paying attention when I talked about
No, oil painting.
oil painting. Oh, what, an audience or an oil painting?
Yeah.
What?
Have you? I've never heard that joke before.
I think that's an old Henny Youngman joke or something like that. You know, comedian tells joke, audience just sits there. So, what is this? An audience or an oil painting? All right. So, but the divergence theorem says that the flux of a vector field through any surface is equal to the integral of the divergence of that same vector field over the volume enclosed by that surface but the divergence is 0 inside that surface, so the divergence theorem seems to be saying that you should get 0 flux because the divergence is 0, and yet we have a non-zero flux. So what's going on here? What's the problem? Well, don't look at your notes, or if you've looked at the notes, you're not allowed the answer. What's the problem here? What could be going on here? Maybe you already looked at the notes. What's that? Q is 0. Yes, that would certainly solve the problem, but in a not particularly interesting way.
That's how I do things.
Right. Well, what were we implicitly assuming when we took this divergence? What happens if R is equal to 0? If R is equal to 0, this is 0 over 0, which is undefined. So in other words, the divergence is 0 everywhere, but maybe not at the origin. And in fact, that's the way it works out, is that the divergence is in fact 0, except at the origin. Our calculation of the divergence breaks down to the origin because we're dividing by 0 at the origin. And so this is how we will be able to fix this. Break down at the origin. So the idea would be that what should be true is that the divergence is infinite at the origin in such a way that when I do the integral, I get Q over epsilon naught. When I integrate the divergence over any volume enclosing the origin, I should get Q over epsilon naught so that it will agree with the flux through that surface. And wanting something which is infinite at a single point and 0 everywhere else, such that its integral gives a finite result, is exactly the sort of thing that we're talking about when we talk about the Dirac delta function. And along these lines, we can point out that also, consider if you've got, say, a point charge, right? What is the charge per unit volume associated with a point charge outside the point charge? 0. How about inside the point charge? Infinity, yes, it's infinity, because if you've got a point charge, it has 0 volume. It's a point, it has 0 volume, and yet it has a finite amount of charge. And so, therefore, the only way you can conceivably get a finite amount of charge from a 0 volume is for the density right at the charge itself to be infinity, right? Right? Charge divided by volume is charge divided by 0 is infinity. So a point charge is also another example of something similar here, where the density associated with the charge is 0 everywhere except infinite at the location of the charge itself, such as I integrate that density over volume. As long as that volume encloses the point charge, it clicks, so to speak, and gives you the value of the charge. So what we're looking for then is in fact the subject of our talk here. We want the Dirac delta function to handle these situations. So the Dirac delta function is defined, quote unquote, by the following properties. It's a delta written like that. So it's a small Greek delta of x is equal to 0 when x is not equal to 0. And it's equal to infinity when x is equal to 0, such that the integral from minus infinity to infinity of delta of x dx is equal to 1. So we'll call this the definition. But we'll put that in quotes because, mathematically speaking, this isn't really a well-defined function per se. In other words, it's not really mapping 0 to some well-defined number. So Dirac defined the delta function and then left it to mathematicians to rigorously produce a theory of these things. And they come from what's called distribution theory. And we're not going to worry about that. We're going to take the physicist's approach and just pretend that we can actually do this, but you can make this rigorous. What's so funny, Ms. Vazicek? It's a deficient. What's the problem here? So my definition was a little deficient. Okay, now it's a definition. And in quantum mechanics, a delta function arises, for example, if you're talking about the wave function of a particle which is at a specific location, the limit of where you actually know the wave function, you know the particle to be at a specific location, its wave function in that case is a delta function. The probability is 0 everywhere except right at its location, where you know it's going to be there. So you integrate the probability distribution, you get 1, just like you're supposed to, and it has the property that the particle's definitely at some location x. Now, we can think of the delta function as being a limit of a sequence of other functions whose properties approach that of the delta function in some limit. And probably the easiest such sequence is a set of box functions. So a box function is just where you have a function, we'll call it b of x, that is 0 everywhere outside some interval of a finite width. And the width of that interval is a from one side of the x-axis, y-axis to the other, so it's a over 2. It goes from x equals minus a over 2 to plus a over 2. And the height of the box is 1 divided by a. So clearly here, the integral of the box function from minus infinity to infinity is just the integral from minus a over 2 to a over 2 of 1 over a dx, or in other words, it's just the area of that rectangle, and that's clearly equal to 1. So the idea is, so to speak, because I say so to speak because really it's not a well-defined limit because of the fact that it blows up at the origin, but take the limit as a goes to 0, and as you do so, the box keeps getting narrower and narrower, but the height is 1 over a, so the height of the box keeps getting taller and taller. So in the limit as a goes to 0, you get an infinitely narrow box, which is infinitely tall, and every box along the way had an area of 1. And so in that limit of sorts, we've created something that has the properties of the delta function. Namely, it's 0 everywhere except right at the origin, where it blows up to infinity, and the integral of it is equal to 1. So you can think of the delta function as being a sort of limit of a sequence of box functions. That's not the only possibility. In fact, there are better things to use that can more readily allow you to talk about the derivative of the delta function, for example, which does show up in some contexts. You can use normalized Gaussians, so bell curves. You can use normalized Gaussians of smaller and smaller sigmas, smaller and smaller widths that blow up in the same sort of limit. You let sigma, the standard deviation of the Gaussian, go to 0, and as you do so, if you let them all be normalized so that the integral is 1, they peak up and become 0 width such that the integral is 1, and it's 0 everywhere except at the origin where it approaches infinity. Okay? Any questions? Wake up! Everybody's looking like this today. It's very disinspiring. I don't even know if that's a word. But it's like, you guys need some caffeine or something. There you go, right there, yes. Ignoring what? Yeah. Delta function has the sifting property. Which is that if I take another function, f of x, multiply it by the delta function, and integrate over all x, then the value is the value of the function at the origin, f of 0. And the way we often describe the sifting property is to say that the delta function clicks at the origin. It clicks and picks out the value of f at the origin. I don't know who came up with that particular description of it, but it's kind of cute. So the delta function clicks and picks out the value of the function at the origin. And we can understand that also in terms of our sequence of box functions. So if here is my function, f of x, and I take some nice narrow box function, then the idea is that as you let the box function get narrower and narrower, it becomes more and more nearly true that f of x is constant over the interval of the box function. And so if I do the integral minus infinity to infinity of the box function of x times f of x dx, well, because it's 0 everywhere outside the interval from minus a over 2 to a over 2 is the box function, then I can just replace my limits with minus a over 2 and plus a over 2. The box function itself is equal to 1 over a in that interval, because that's how we define the box function. It's a wide and 1 over a tall. So the box function is equal to 1 over a. So it's 1 over a f of x dx. But if a is small, then f of x is very nearly constant over the interval where the box function does not vanish. And so we can pull that very nearly constant value out. Namely, it's very nearly equal to its value at the origin, since the interval is shrinking around the origin. So it's approximately 1 over a f of 0 times the integral from minus a over 2 to a over 2 of 1 over a dx, which is, of course, just 1. That's just the box function by itself. I mean, whoops, I pulled the a out of, okay, so I'll just leave it this one. So f of 0 times the integral of the box function, sorry, minus a over 2 to a over 2, 1 over a dx. This integral is equal to 1, and so we just get f of 0 in the limit that we let the box function shrink to 0 with. So this sequence of box functions has this property in the limit as the functions become narrower and taller. And the delta function is, quote unquote, defined to be the limit as a goes to 0, and so the delta function does have that property in that limit. Okay, happiness and joy? Yeah, yes, all right. So, one more thing we need, and that is to allow our delta function to live somewhere else besides just at the origin. After all, if we're going to use it to represent point charges and so forth, they have to be able to live anywhere. And then we'll also jump to 3 dimensions momentarily. And that is to say that delta of x minus a is a delta function which spikes. We call the jump to infinity spiking, and we call it a delta spike often, is a delta function which spikes at x equals a instead of at the origin. And so to represent that, we'll often draw, here's an x-axis, here's the point x equals a, and to represent the delta function, we draw a little arrow there to say, there it is, shooting up to infinity. It's 0 everywhere else, but it's shooting up to infinity right at x equals a. Why is this true? Why does making delta of x minus a produce a delta function that peaks at a instead of at 0? Yeah?
Because when x equals a, you don't go to 0.
Right, exactly. In other words, the delta function is defined so that it spikes when its argument is equal to 0. So the argument of delta of x minus a is equal to 0 when x is equal to a, and so therefore that's why it peaks up at x equals a. In general, if you take any function f of x minus a, that shifts that function a to the right, and that's exactly what we've done here. It's the same sort of argument. So the sifting property in that case becomes integral of f of x times delta of x minus a dx is equal to f of a. The delta function clicks at a in that case and picks out the value of the function at a. Well, we dwellers of a, at least seemingly, 3-dimensional universe, maybe there's 10 or 11 dimensions, but at least there seems like 3 in classical E&M, it's got 3 dimensions. So at least our pretend model world has 3 dimensions. We want to have a delta function to work in 3 dimensions, and to create that beast, we we make the three-dimensional delta function, three-dimensional Dirac delta function, delta 3 of r with the vector argument there is just equal to product of three one-dimensional delta functions, delta of x, delta of y, delta of z. And excuse me, we can also then talk about delta 3 of r minus a and that spikes at r equals a. That's infinity at r equals a and 0 everywhere else. And just like our one-dimensional Dirac delta function, if we integrate over all space, that gives us 1. And it doesn't matter if you shift the argument and make it r minus a, that also gives you 1. So the integral over all space of the three-dimensional Dirac delta function is 1, and it has the sifting property analogous to the one-dimensional Dirac delta function. Namely, take any function and integrate it against the Dirac delta function in 3 dimensions with respect to volume, and it clicks and gives you the value of the function at a. So there's a 3-dimensional version which works just like the one-dimensional version does. And so this lets us say that if we have a point charge that we can be more specific than to just say that its density is infinite at the location of the charge. What we can say is that if we have a point charge q, then that is located at r equals a. So it's located at some position vector a, then the charge density associated with that point charge, rho as a function of r, is just equal to q times the 3-dimensional Dirac delta function with argument of r minus a. So this is, in a sense, saying that the charge density is 0 everywhere, except right at r equals a, the location of the charge, where it's equal to q times infinity, so to speak, such that if you integrate the charge density, well, that'll just be, we integrate over all space if we like, although all we have to do is have our volume include the charge, because the density is 0 everywhere outside the charge. But all space works, but you can also just any volume that encloses the charge. If I do the integral, then I'm doing q times Dirac delta function. And q is a constant that can be pulled out of the integral. The integral itself is equal to 1. And so you just get q. You integrate the charge density. So this encapsulates the idea that a point charge has infinite charge density, and if I integrate its charge density over any volume that encloses it, I'll just get the charge. If the volume doesn't enclose the charge, the density is 0 everywhere inside that volume, and you get 0 in that case. So the Dirac delta function gives us a way of handling a situation like that, where you've got a point charge and you need to represent what its charge density is. 0 everywhere except right at the charge where it's infinity. Questions? And always remember, what are you talking about is a legitimate question. If you don't understand what's going on, you should say that. Yes?
Okay, why is the everything but Q
Why is the integral 1? Okay, so again, you have to think of this as the Dirac delta function, okay? So, you know, we've defined it to have this property that its integral over all space is equal to 1. But then, but see, in this case, see, you know, I could go like this. I can say this is Q, just to continue this, I can say over all space of Dirac delta function, okay? So, okay, F is, I'm multiplying the Dirac delta function by the function 1, right? And so the value of the function 1 at r equals a is 1, if you like, and so that would be one way to say that the integral is 1. More fundamentally here, though, the integral of a Dirac delta function over, in 1 dimension, the whole line, in 2 dimensions, the whole plane, or in 3 dimensions, all of space, the integral of the Dirac delta function is always equal to 1. So the integral itself, just by definition, basically, is 1. And so you just get Q, since you multiply that. If you wanted to do the 2-dimensional, you know, so you understand in the 1-dimensional Dirac delta function, the sequence of box functions, how that's working, okay? In 2 dimensions, what you would do is to have, instead of a simple 1-dimensional box like that, you'd have a 2-dimensional box. So if this is the XY plane here, and then you imagine the z-axis coming out of the board, and you had some point with position vector A, then you draw a little square, if you like, around that point, whose width was A on both sides, and then you'd have sticking up above that, creating an R-par, a box, whose height was equal to, let's see, in this case, we want the volume enclosed to be always 1. So this is A squared, so its height would have, excuse me, would have to be equal to 1 divided by A squared instead of 1 over A. And then you'd let the size of this square shrink to 0, and so you'd have this rectangular pencil, if you will, that got taller and taller as the sides got smaller and smaller. And that would always have a volume enclosed. If you do an integral dx dy, it's the volume under the curve that you would plot along the z-axis. So the volume under the box function would always be 1 in that case, and so you'd be taking that limit. In 3 dimensions, well, then you just make a 4th axis perpendicular to the 3 dimensions of space. And so you take a little cube and go off in the 4th dimension, and you'll have this hypervolume underneath the volume that would be your box function, and that would always equal 1. You know, generalizes to any number of dimensions. Thinking in terms of, if we're doing in 2 dimensions, you do delta of x, delta of y, and that's really what we've done here. We've multiplied 2 1-dimensional box functions by one another. And so you get something which is A by A, if you make them always have that. You could have an A and a B if you wanted, but you always keep them both having the same width. You'd have an A by A on the bottom here, and then the height would be 1 over A times 1 over A, because each box function is 1 over A tall in each direction. So it'd be 1 over A squared high, and A squared in area at the base, such that the volume is always 1. In 3 dimensions, just go up one more. It's A by A by A, 1 over A cubed high off in the 4th direction. That's perpendicular to the 3 directions of space, because we want to plot it 4 dimensions in that case. But, you know, mathematically speaking, that makes perfect good sense. So our 3-dimensional box function is a product of 3 1-dimensional box functions. Our 3-dimensional delta function then can be thought in that limit as a product of 3 1-dimensional delta functions, 1 for each direction. And so in this case, the integral is, we've set it up so that the integral of the delta function is always 1. It's infinite at one point such that its integral is 1 as long as that point is in the interval of integration. And so here we could just factor out the q, and so we get q times 1 when we do the integral. Or if you like, if you want to view this as being the function that is multiplied by the delta function. This is a constant function. Its value is equal to q everywhere in the universe. And so its value is also equal to q at r equals a. And so the sifting function says, pick out the value of this function, which is constant everywhere at the location of the point charge. Well, that's q. So either way, sifting property or just the fact that the delta function integrates to 1, either way, you get the same thing. The interval is q. Okay. Any other questions? All right. Then let's look at that divergence piece again. So we've got for our electric field of the point charge at the origin, q over 4 pi epsilon naught r squared r hat. We saw that div E equals 0, except maybe at the origin, because there we're dividing by r equals 0, and that's not kosher. So div E was 0 everywhere, except maybe not at the origin. Meanwhile, we saw that div E d tau, which is equal to the flux out of any surface surrounding the origin, is in fact equal to q over epsilon naught. The flux is q over epsilon naught. So we're going to want to define the divergence such that its integral over the volume enclosed by any surface surrounding the origin is equal to q over epsilon naught. If we decide that, yeah, the divergence isn't 0 at the origin, such that when I integrate it, I get q over epsilon naught for any volume that contains the origin, this is telling us the divergence is a Dirac delta function. Right? In other words, the divergence is 0 everywhere, but it has a finite integral. 0 everywhere except at one point, and has a finite integral. That means it's a Dirac delta function, or it's a multiple of a Dirac delta function. It has exactly the properties that we've decided that a Dirac delta function has. So do a little, what is this from? Mary Poppins? I can't remember. You guys are dead today, so I thought I need to like so put them together, and what have you got? You guys know it all, and now you're just looking like I'm completely lost my mind. All right, well that's probably true, but anyway, no, bippity boppity. You ever heard that before?
Yeah, it's
Right. Okay. What's that from? What's that?
Cinderella, right?
What?
Cinderella.
Is that Cinderella?
Yeah.
Oh, that's Cinderella. Okay.
I'd say
Okay, it's not Mary Poppins. I couldn't
She's
remember.
like up
That's
there.
how
Right. So that's how I threw you. Well, as I said, is it Cinderella? I mean, is it Mary Poppins? I was tragically in error, but yeah, okay. So anyway, so you got these facts, put them together, and what have you got? You've got that div E equals q over epsilon naught delta 3 of r. That'll give you what you want. If div E is q over epsilon naught delta 3 of r, well then when I integrate div E over any volume that contains r equals 0, where the delta function is spiking, then I'll get q over epsilon naught. Because the integral of the delta function is 1, and so q over epsilon naught times the delta function integrates to q over epsilon naught. And thus we deduce that the divergence of q over 4 pi epsilon naught r squared r hat, which is what E actually is in that case, is equal to q over epsilon naught times the three-dimensional Dirac delta function. And so that means that if we just want the divergence of r hat over r squared by itself, then we can cancel the Q over epsilon naught and throw the 4 pi to the other side and deduce that the divergence is equal to 4 pi times the 3-dimensional Dirac delta function. So this solves the conundrum of that mysterious problem where you saw that the divergence was 0, and yet strangely enough that thing is everywhere pointing away from the origin. So it seems like it's got divergence, but the divergence is 0. What's up with that? It's because the divergence is 0 everywhere except at the origin, where it's infinite, such that the divergence is actually 4 pi times the delta function. And or B, we no longer have a conundrum anymore. It was only an apparent conundrum. Wow. It was only an apparent conundrum, and we saved it by merely defining a function which doesn't really exist in order to take care of the situation. But it does exist as a distribution, and physicists don't really care. We really do just kind of think of delta functions as being real, and that's okay. Okay, any questions? Yes?
So does that have any like physical significance, or is it just math?
It has physical significance because, remember, we're doing E and M here. And so for the delta function, for the charge density for a point charge, I mean, that makes perfectly good sense, right? In other words, that the charge density should be infinite except infinite right at the charge and 0 everywhere else. So, you know, that's intuitively reasonable. This also basically is conveying this idea that if I draw the field around the point charge, that we're getting something like this. So, you know, it's falling away as you get further away from it. And if I draw, say, 2 spheres surrounding that charge. So we've got a spherical shell. There's an inner surface, there's an outer surface of the spherical shell. The divergence being 0 everywhere inside the spherical shell means if I integrate the divergence, I'll get 0. So there's no flux through the surface. Well, that works out because the flux into the inside surface is exactly with the flux out of the outside surface. And so as long as your enclosing, as long as your closed surface doesn't have the origin inside of it, then hunky-dory, it's perfectly reasonable that the divergence is 0 because you get as much inwards flux as outwards flux. But as soon as you get rid of that inner surface and poof, make this point, the origin, be inside your enclosing volume, that's when there's no inner surface to cancel the flux through the outer surface. So the only flux there is this flux through the outer surface. And no matter how much I shrink that outer surface, no matter how close I shrink it down to the origin, as long as it surrounds the origin, there's stuff coming out. If you think in terms of our fluid mechanics analogy, this is the end of a hose pumping fluid from another dimension into our swimming pool or whatever. This indicates that the situation I've described obtains, basically. That when you get right to the origin, the divergence blows up because right at the origin is the source of this fluid, or the source of electric field. And so that's really the way to think of it, is that the delta function here is saying there's a point source at that location. That's what that is telling us. Okay. Any other questions? And it's 10 till. That's right, yes. Okay. How did this get so short, by the way? I'm glad. This little thing here, it was huge. Okay. Before we actually move into doing some electromagnetism, well, we've done a little bit, but one more thing. You already met this beast in your homework, but we should point out this notation that the author of your textbook uses for the source point, the field point, and the separation vector. So in other words, E&M is all about taking a distribution of charges or currents and calculating what the electric and magnetic fields are due to those charges and or currents. And so, in general, we'll have some point where we're trying to figure out what the electric and magnetic field are, and that'll be due to charges and currents. So we talk about, if here's a charge Q that's serving as a source of field, then that's the source point, and it's got position vector r prime. And meanwhile, where we're actually trying to calculate the field is the field point, which is r, and the separation vector, which points from the source point to the field point, and is r minus r prime, like that. And in most of the literature and in most books, you just leave that as r minus r prime. Your author, Griffiths, likes to use this notation that r minus r prime is kind of a script r like that, the separation vector. And I think that's a good idea, actually. It simplifies a lot of expressions. But it means you have to be careful and not think that you can take it out of integrals, is what it comes down to. That's the temptation, is to think that it's a constant that can be factored out of integrals, and it isn't, because in general you're integrating over some charge distribution or summing over a bunch of charges, and so the value of r prime keeps changing as you move from one part of the charge distribution to another, which means that r, script r here, is not a constant. It doesn't come out of integrals. So if you pull it out of an integral, that's a way to just say, Dr. Harmon, I didn't really want any points on this homework problem anyway. So presuming that's not how you feel, then you shouldn't do that. So field point, source point, separation vector between the two. And one of the sorts of things that it simplifies writing is if you find the electric field due to Q, then you can just say that it's Q over 4 pi epsilon naught script r squared script r hat. In other words, it's just the separation vector just treats Q as though it was the origin, essentially, and so then the electric field is just distance from the origin sitting at Q, r squared, and then r hat is the unit vector, which points away from Q. Notice that r hat is defined so that it points away from Q, because r points from Q, script r points from Q to whatever field point you're talking about. This is what we want, that the electric field points away from Q if it's positive and points towards Q if it's negative. If it's negative, you get minus r hat, which would be pointing in the direction of Q. And of course, it also means you have to be careful, and I have to be careful. You know, I'll say R and not remember to say script R instead. So if what I'm saying is truly ambiguous, like you can't figure out which one I mean, then you just say, is that script R or is that not script R, Dr. Harmon, or something like that. If we don't use that notation, well then what we would do instead, and what you'll often see, is notice that you can rewrite that, whoops, bad me. You can rewrite that as just multiply and divide by script r magnitude. Script r magnitude times r hat is just the vector script r without the unit vector business. You know, it's just a vector itself instead of the normal vector in that direction. But once I've divided by r, this has to be an r cubed right there. So another way to write Coulomb's law is Q over 4 pi epsilon naught r cubed times r instead of r hat. And if you don't use this script notation, then the way you'll often see this written as is Q over 4 pi epsilon naught times the magnitude of r minus r prime cubed times the vector R minus R prime. So this is what you'll often see written instead of putting it like this. So I like what the author does with that. But again, don't allow that to tempt you to pull things out of integrals that do not get to be pulled out of integrals. Okay, any questions? All right, then it's time to move on to chapter 2, wherein we will actually talk about electrostatics now. So that's how we'll start, electrostatics. And there was much giggling in the background.
I started chapter 2 early, my notes.
Oh, you did? Oh, okay. Well, that's okay. Wow. Suddenly got a little colder. Oh. So, it's time for electrostatics. Or in other words, we just want to figure out what's the electric field of a bunch of point charges just sitting around. As opposed to electrodynamics, if you got weakly point charges, moving point charges, you can get a time-varying electric field. But now we're just going to have a nice, static, stationary, not time-varying electric field. So, as you well know, and as we've even mentioned already, even today, then if you've got a pair of charges, and we'll call them little q and big Q, no implication as to which one's actually greater charge, just different names. If we make our script R go from little q to big Q, like that, separation vector like that, and our rule here is that R is always going to point from the other charge to the charge on which the force is to be calculated, we're about to find the force on Q. F sub Q, force on charge big Q, is equal to the product of the charges divided by 4 pi epsilon naught times their separation squared, R squared, times R hat. So note here the rule is always R hat always points from the other charge to the charge on which we're finding the force. So what this is saying is then if I drew a little, I could draw this again. Here's Q little q and equally Q big Q. You don't have to make one feel bad. Then our R hat there points away from the source charge, if you will, the charge which is doing the exerting, and so the force that we're the charge that we're calculating the force on, a little R hat, points away from the other charge, which is the point, and it's the product of the charges. So that means that the two charges are both positive, or if the two charges are both negative, then we're getting a repulsion. The force is along R hat and therefore away from the other charge. Or if one is positive and the other is negative, it's an attractive force because then the force points opposite to the direction of R hat, or in other words, towards the other charge. So this embodies the idea that like charges attract and opposite charges, that like charges repel and opposite charges attract. Just being sure if I'm paying attention. We want to claim I'm being sure that you're paying attention. And furthermore, if we found the force on Q, then we would make the R hat point in the other direction, right? Because it always points from the other charge to the charge that you're finding the force on. The magnitude is the same, but the direction will be opposite because the R hat flips sign. It turns around. Or in other words, Coulomb's law obeys what? Grand physical principle formulated by a great physicist, which we think all forces described in nature obey. Newton's third law. Yeah, that's Newton's third law. Coulomb's law has built into it that it obeys Newton's third law, because if you switch the order of the charges, you flip the direction of the arrow. And so equal and opposite forces is what two charges exert on one another. They're both repelling each other or both attracting each other with equal strengths. Okay? Now, again, this is not new to you. You certainly know that because of the way this thing works, that we could do the following. We could say, well, the force on Q is certainly equal to charge Q itself, the charge on Q itself, multiplied by the quantity, Q over 4 pi epsilon naught, squiggle R squared, I accidentally made it a regular R in my notes there, times R hat. And then we define that to be Q times the electric field at the location of Q. That's the electric field at the location of big Q due to little q. So in other words, we say little q sets up an electric field around itself, given by q over 4 pi epsilon, little q over 4 pi epsilon naught r squared times r hat. And this solves the conundrum, if we're willing to believe that this electric field is real, of how do the charges know one another are there? In other words, how do they communicate their presence to each other? So what we say is, the way that big Q knows that little q is there is that little q sets up an electric field around itself. And what big Q is actually responding to is not little q itself directly, but to the electric field at its location. And so this eliminates the problem of action at a distance. But on the other hand, you also ask yourself, is the electric field real, or is it just this convenient fiction that we're inventing in order to get rid of action at a distance, but now we've introduced this mysterious other thing into the problem. Does that other thing really exist? And the answer, most physicists would say, is yes, the electric field really exists. If all we ever did was electrostatics, then you really couldn't give a firm answer to the question. All you could do is say, well, we could take either point of view, and it doesn't hurt to talk about electric fields, so we might as well pretend it exists, even if we're not sure there really is such a thing. However, the world isn't just static. Charges move around, and it's the fact that charges can move around that convinces us that electric fields are real, that they have their own separate existence, that it's not just this convenient way of rewriting Coulomb's law. Because, for example, according to Coulomb's law, then suppose that Q moves location. All right? If Q is moving, what's happening to R hat? If little q is moving, what's happening to R hat? It's changing, right? It's following along, okay? And what does Coulomb's law predict? If I move little q, according to Coulomb's law, when does big Q feel it? When does it have an effect on big Q if I move little q? According to Coulomb's law, if you just read it as written, what is it saying? What's that? Come on, be bold. Right away is the answer, yes. See, you are a genius.
I'm bold.
You are bold and a genius, yes. Coulomb's law is saying that right away, big Q will feel any change in the position of little q because instantly, R hat here is the instantaneous unit vector that points away from the instantaneous location of little q to the instantaneous location of big Q. So Coulomb's law says that the effect of moving little q is instantly felt at big Q. See any problem with that based on other things you may have learned in physics classes? The speed of light, yes. According to Coulomb's law, then somebody on Jupiter could go with a little charge, and if we had a sufficiently sensitive detector, our detector would go right away. And so, for example, we could say, prepare your defenses, the Jovians are launching the invasion fleet right now. And we would instantly know that we need to prepare our defenses. And yet, we know it doesn't work that way. That the fastest that signals can propagate is the speed of light. Now, of course, Einstein got to that by considering electromagnetism. And so this wasn't such a shocker. The shocker was that electromagnetic fields travel at the speed of light in a vacuum no matter what, and there's no frame of reference that's objectively at rest, and so on and so forth. But in other words, it was already known before Einstein that if you move a charge around, the effects aren't instantly felt elsewhere. Coulomb's law was known already to only apply to electrostatics, not to the situation of charges in motion. So I'm not implying that Einstein discovered that Coulomb's law was only for electrostatics. That was already known. But it's the fact that the effects of Q are not, the effects of moving little q aren't instantly felt at big Q, which is probably the best clue that the electric field is real. And so we'll do two things. First, we'll watch a little movie clip that sort of is fun, you know, from The Elegant Universe with Brian Greene, that talks about a similar idea with gravity. Because in gravity, right, what's the expression for the force of gravity between two masses? If I've got little m and big M, then the force on big M is equal to, yeah, big G times little m times big M over, let's see, if I call their separation vector R like that, it's over R squared times, but I'm missing something. There's still the R hat. I'm missing one little thing here. -1. That's right. They're attracting. Yes, they're attracting. Masses are always attracting. So in other words, Newton's law of gravity looks exactly like Coulomb's law, other than the fact that you've got only one kind of mass and it's always attractive. So you throw in a -1, and you got G instead of 1 over 4 pi epsilon naught. But mathematically, they're identical. So Newtonian gravity obeys Gauss's law just as surely as the electric field, for example, obeys Gauss's law. The flux of the gravitational field through a surface is proportional to the total mass inside that surface, et cetera, et cetera. Fundamentally, they're both inverse square laws that involve the force only being along the line joining the particles. So, big analogy there. Well, according to Newton's law of gravity, if one of the mass moves, the other one instantly feels it. That would violate the principle of relativity. And so Einstein got around that conundrum by inventing general relativity and showing that gravity is a ripple in space, is a curvature of space-time, and that if you move something, it causes a gravitational wave to propagate out before and so its effects are only felt when the gravitational wave gets to the other mass. So let's show Newton's embarrassing secret.
I'm sure it's very nice.
Yeah. That Newton would have done. Let's see. This will work better if I unblack the screen. And no, thanks for Dell support, but I'm not looking for convenient for support tools in one convenient location. Ah, they're so obnoxious. Sure. All right. Well, I'll tell you what. Later on, you can. All right. Here we go. Here we go.
As the story goes, one day in 1665, a young man was sitting under a tree when all of a sudden he saw an apple fall from above. And with the fall of that apple, Isaac Newton revolutionized our picture of the universe.
In an audacious proposal for his time, Newton proclaimed that the force pulling apples to the ground and the force keeping the moon in orbit around the Earth were actually one and the same. In one fell swoop, Newton unified the heavens and the Earth in a single theory he called gravity.
The unification of the celestial with the terrestrial, that the same laws that govern the planets in their motions govern the tides and the falling of fruit here on Earth. It was the fantastic unification of our picture of nature.
Gravity was the first force to be understood scientifically, though 3 more would eventually follow. And although Newton discovered his law of gravity more than 300 years ago, his equations describing this force made such accurate predictions that we still make use of them today.
In fact, scientists needed nothing more than Newton's equations to plot the course of a rocket that landed men on the moon. Yet, there was a problem. While his laws described the strength of gravity with great accuracy, Newton was harboring an embarrassing secret. He had no idea how gravity actually works. For nearly 250 years, scientists were content to look the other way when confronted with this mystery. But in the early 1900s, an unknown clerk working in the Swiss Patent Office would change all that. While reviewing patent applications, Albert Einstein was also pondering the behavior of light. And little did Einstein know that his musings on light would lead him to solve Newton's mystery of what gravity is. At the age of 26, Einstein made a startling discovery: that the velocity of light is a kind of cosmic speed limit, a speed that nothing in the universe can exceed. But no sooner had the young Einstein published this idea than he found himself squaring off with the father of gravity. The trouble was, the idea that nothing can go faster than the speed of light flew in the face of Newton's picture of gravity. To understand this conflict, we have to run a few experiments. And to begin with, let's create a cosmic catastrophe. Imagine that all of a sudden, and without any warning, the sun vaporizes and completely disappears. Now, let's replay that catastrophe and see what effect it would have on the planets according to Newton. Newton's theory predicts that with the destruction of the sun, the planets would immediately fly out of their orbits, careening off into space.
In other words, Newton thought that gravity was a force that acts instantaneously across any distance, and so we would immediately feel the effect of the sun's destruction. But Einstein saw a big problem with Newton's theory.
A problem that arose from his work with light. Einstein knew light doesn't travel instantaneously. In fact, it takes 8 minutes for the sun's rays to travel the 93 million miles to the Earth. And since he had shown that nothing, not even gravity, can travel faster than light, how could the Earth be released from orbit before the darkness resulting from the sun's disappearance reached our eyes? To the young upstart from the Swiss Patent Office, anything outrunning light was impossible. And that meant the 250-year-old Newtonian picture of gravity was wrong.
if Newton is wrong, then why do the planets stay up? Because remember, the triumph of Newton's equations come from the quest to understand the planets and the stars. In particular, the problem of why do the planets have the orbits that they do. And with Newton's equations, you can calculate the way that the planets will move. Einstein's got to resolve this dilemma.
In his late 20s, Einstein had to come up with a new picture of the universe in which gravity does not exceed the cosmic speed limit. Still working his day job in the patent office, Einstein embarked on a solitary quest to solve this mystery. After nearly 10 years of racking his brains, he found the answer in a new kind of unification.
Einstein came to think of the three dimensions of space and the single dimension of time as bound together in a single fabric of space-time. It was his hope that by understanding the geometry of this four-dimensional fabric of space-time, that he could simply talk about things moving along surfaces in this space-time fabric.
Like the surface of a trampoline, this unified fabric is warped and stretched by heavy objects like planets and stars. And it's this warping or curving of space-time that creates what we feel as gravity.
A planet like the Earth is kept in orbit not because the sun reaches out and instantaneously grabs hold of it, as Newton's theory, but simply because it follows curves in the spatial fabric caused by the sun's presence. So, with this new understanding of gravity, let's rerun the cosmic catastrophe. Let's see what happens now
If the sun disappears. The gravitational disturbance that results will form a wave that travels across the spatial fabric in much the same way that a pebble dropped into a pond makes ripples that travel across the surface of the water. So we wouldn't feel a change in our orbit around the sun until this wave reached the Earth. What's more, Einstein calculated that these ripples of gravity travel at exactly the speed of light.
And so, with this new approach, Einstein resolved the conflict with Newton over how fast gravity travels. And more than that, Einstein gave the world a new picture for what the force of gravity actually is. It's warps and curves in the fabric of space and time.
Einstein called this new picture of gravity general relativity. And within a few short years, Albert Einstein became a household name.
Einstein was like a rock star in his day. He was one of the most widely known and recognizable figures alive. He and perhaps Charlie Chaplin were the reigning kings of the popular media.
People followed his work, and they were anticipating, because of this wonderful thing he had done with general relativity, this recasting the laws of gravity out of his head. There was the thought he could do it again, and people want to be in on that.
Despite all that he had achieved, Einstein wasn't satisfied.
He immediately set his sights on an even grander goal, the unification of his new picture of gravity with the only other force known at the time, electromagnetism.
Now, electromagnetism is a force that had itself been unified only a few decades earlier. In the mid-1800s, electricity and magnetism were sparking scientists' interest. These two forces seemed to share a curious relationship that inventors like Samuel Morse were taking advantage of in newfangled devices such as the telegraph. An electrical pulse sent through a telegraph wire to a magnet thousands of miles away produced the familiar dots and dashes of Morse code that allowed messages to be transmitted across the continent in a fraction of a second. Although the telegraph was a sensation, the fundamental science driving it remained something of a mystery. But to a Scottish scientist named James Clerk Maxwell, the relationship between electricity and magnetism was so obvious in nature that it demanded unification. If you've ever been on top of a mountain during a thunderstorm, you'll get the idea of how electricity and magnetism are closely related.
When a stream of electrically charged particles flows, like in a bolt of lightning, it creates a magnetic field, and you can see evidence of this
on a compass. Obsessed with this relationship, the Scot was determined to explain the connection between electricity and magnetism in the language of mathematics. Casting new light on the subject, Maxwell devised a set of 4 elegant mathematical equations that unified electricity and magnetism in a single force called electromagnetism. And like Isaac Newton before him, Maxwell's unification took science a step closer to cracking the code of the universe.
That was really the remarkable thing, that these different phenomena were really connected in this way. And it's another example of diverse phenomena coming from a single underlying building block or a single underlying principle.
Imagine that everything that you can think of that has to do with electricity and magnetism can all be written 4 very simple equations. Isn't that incredible? Isn't that amazing? I call that elegant.
Einstein thought that this was one of the triumphant moments of all of physics and admired Maxwell hugely for what he had done.
About 50 years after Maxwell unified electricity and magnetism, Einstein was confident that if he could unify his new theory of gravity with Maxwell's electromagnetism, he'd be able to formulate a master equation that could describe everything, the entire universe.
Einstein clearly believes that the universe has an overall grand and beautiful pattern to the way that it works. And so to answer the question, why was he looking for the unification? I think the answer is simply that Einstein is one of those physicists who really wants to know the mind of God, which means the entire picture.
Today, this is the goal of string theory: to unify our understanding of everything, from the birth of the universe to the majestic swirl of galaxies, in just one set of principles, one master equation. Newton had unified the heavens and the earth in the theory of gravity. Maxwell had unified electricity and magnetism. Einstein reasoned all that remained to build a theory of everything, a single theory that could encompass all the laws of the universe, was to merge his new picture of gravity with electromagnetism.
He certainly had motivation. Probably one of them might have been aesthetics or this quest to simplify. Another one might have been just the physical fact that it seems like the speed of gravity is equal to the speed of light. So if they both go at the same speed, then maybe that's an indication of some underlying symmetry.
But as Einstein began trying to unite gravity and electromagnetism, he would find that the difference in strength between these two forces would outweigh their similarities. Let me show you what I mean. We tend to think that gravity is a powerful force. After all, it's the force that right now is anchoring me to this ledge.
But compared to electromagnetism, it's actually terribly feeble. In fact, there's a simple little test to show this. Imagine that I was to leap from this rather tall building. Actually, let's not just imagine it. Do it. You'll see what I mean.
Now, of course, I really should have been flattened, but the important question is, what kept me from crashing through the sidewalk and hurtling right down to the center of the earth?
Well, strange as it sounds, the answer is electromagnetism. Everything we can see, from you and me to the sidewalk, is made of tiny bits of matter called atoms. And the outer shell of every atom contains a negative electrical charge. So when my atoms collide with the atoms in the cement, these electrical charges repel each other with such strength that just a little piece of sidewalk can resist the entire Earth's gravity and stop me from falling. In fact, the electromagnetic force is billions and billions of times stronger than gravity.
That seems a little strange because gravity keeps our feet to the ground, it keeps the Earth going around the sun. But in actual fact, it manages to do that only because it acts on huge, enormous conglomerates of matter. You know, you, me, the Earth, the sun. But really at the level of individual atoms, gravity is a really incredibly feeble, tiny force.
It would be an uphill battle for Einstein to unify these two forces of wildly different strengths. And to make matters worse, barely had he begun before sweeping changes in the world of physics would leave him behind.
Einstein had achieved so much in the years up to about 1920 that he naturally expected that he could go on by playing the same theoretical games and go on achieving great things. And he couldn't. Nature revealed itself in other ways in the 1920s and 1930s, and the particular tricks and tools that Einstein had at his disposal that had been so fabulously successful just weren't applicable anymore.
You see, in the
I know, it's fun, but we have to continue on with E&M, but, so I know. What's that? Oh. Up screen. You know, that entire thing's available online. You can go to pbs.org and you can watch the entire 3 hours of Universe. Wow. Or watch it as an SPS movie night or something. Because as you can see, it's really good if you haven't seen it. So kind of continuing along those lines, you know, where he showed the sun disappears and Newton would have predicted that instantly the planets would fly out of their orbits, because instantly, if the sun disappeared, there'd be no longer any force on the planets. And you know that when there's no force on an object, then the way that it moves is in a straight line at constant speed. So as soon as you cut the force, the planets would fly off in straight lines at constant speed, except for their small gravitational interactions with each other. According to general relativity, that's not what would happen. If the sun disappeared, that would create a gravitational wave that traveled out, and this formerly curved space-time would become flat, and only when that wave passed by Earth would we notice that the sun had disappeared, and thus would Earth's orbit be changed, would it start to fly off. Well, the same sort of thing is true about the electromagnetic field. And again, this was known before Einstein. It was already known because Maxwell had achieved his unification in the 1860s. And in fact, you know, the goal of this course is to get us up to the 1860s is what it comes down to set forth the very first unified field theory that was produced by physicists In fact, Maxwell didn't invent Maxwell's equations. They were invented by other people, except for one very crucial term that he added that produced a unified set of equations. And so that's our goal, is to eventually get to Maxwell's equations and get you to understand what they mean in both their differential and integral forms, or in both their differential and integral forms, to put the proper accent on things. But along the way, let's find the piece of my notes that I was looking for here. I hate it when that happens. If you got my notes, you can look on page 29, and that's what I'm about to try to draw on the board here. What's 28 say? I don't remember. Yeah. 28. It's not important. 28. See, my notes got this kind of. Oh yeah. Okay. Well, yeah. Right. So we can draw the electric field right around the point charge, and you did something similar in the homework already, where you were sketching r hat over r squared, and as some of you asked me the question about it, I pointed out, well, it's like sketching an electric field around the point charge. In other words, since it's spherically symmetric, it's convenient to draw the vectors and circles surrounding it. So you just draw arrows to represent the magnitude and direction of the electric field at various points, and the field points radially away from the charge. So if I draw this carefully, all these arrows have the same length. And then furthermore, if it's obeying Coulomb's law, then if I get twice as far from the charge, the field's only 1/4 as strong. Well, I've drawn these arrows so long I can't even do that. So let's get 3 times as far from the charge, in which case the arrows are only 1/9 as long. So actually, what people tend to do when they're sketching something like this is not show just how rapidly the electric field is in fact falling off. If I'm 3 times further away, the arrows have gotten only 1/9 as big, so the lengths of the arrows really do fall off quickly. But you could also represent the electric field in terms of electric field lines. And electric field lines are drawn such that the electric field is tangent to the field line at every point. So for a situation like this, a charge at the origin, then since the electric field is everywhere pointing radially outwards, if we draw electric field lines, we'll draw them as a bunch of lines that all come together at the point Q. Now, how many field lines does the charge have? 42, that's correct. There are 42. No, in fact, there are an infinity of field lines, which would get kind of tedious to draw, so we draw a subset of them. And we like to, I'll get busy here. And so this is field line number 6,543, 75 million years later. And this is field line. What's that? Oh yeah. And this is. And then we draw arrows on the field lines to indicate which direction the electric field is pointing at those locations. And so the spreading of the field lines, that they're getting further apart, is indicating the diminution of the electric field in this case. Now this is for the static situation. Suppose that we make the charge move. Well, it turns out that if you solve Maxwell's equations, so again, Einstein didn't discover this, this was well known before. If you solve Maxwell's equations for the case of accelerating charges, then the result is that you find that it produces electromagnetic waves, disturbances in the electric and magnetic field that propagate away from the charge at the speed of light. Well, in particular, what would happen if I take my charge and I very rapidly move it to another location and then let it sit there? So I just say, ooh, and then it just stays there after that, okay? Well, what happens is that the disturbance starts propagating away from the charge at the speed of light. And so if you are further away than a light wave could have traveled since the charge was moved, the electric field still looks the same as it did when Q was sitting here, because you haven't yet had time to get that information that the charge has moved yet. So if you're 5 light years away and I move the charge today, it's going to be 5 years from now before the field 5 light years away looks any different from what it does now from the charge. And so I rip the charge over and then I suddenly stop it. When I suddenly stop it, then the electric field inside of a region which could be reached by a light wave since the time the charge stopped would be described by an electric field that obeys Coulomb's law for the charge at that location. So in other words, what you get looks like this, which took me a while to draw, so I'll draw a rough version of it here. The idea is that if I quickly move this charge to another location, so here's the original charge position, here's the final location of the charge over here, so here's the initial point, the final point, then let's say that by the time in question, I'm looking at some instant when a light wave which started at point F would have gotten that far, out to the radius of that circle right there. So in other words, if the time I'm observing now is t, and t sub final is when the charge reached this location, then this would be a circle of radius c times t minus t final. In other words, the speed of light times the time since the charge got to location F. Inside that sphere, the electric field of the charge looks just like it would for good old Coulomb's law. In other words, nice radially pointing field lines described by Coulomb's law, like that. Meanwhile, let's say that since the charge moved, that a light wave had time to go, say, since the charge initially started moving, the light wave starting at that location would have had time to get out to there, which is supposed to be a sphere centered on I, which it isn't. But in any case, the idea would be that outside that sphere, the electric field would look exactly like Coulomb's law for a charge located at I. Outside a sphere, such that light which traveled from I at the instant that the charge was moved had not yet had time to reach it. So this would be the boundary that a light wave could have reached since the time that I was moved. Outside that sphere where light hasn't had time to reach yet, the electric field would look just like it did before the charge moved. In other words, it would be Coulomb's law for a charge located at point I would describe the electric field. And then, in the region in between, you have to match up the field lines in the inner region and the outer region. And I don't really have time to draw that here, but I did draw it nicely in my notes. The details of how the field lines match up would actually depend on the details of how the charge moved. But the point is that there would be a region in between these two spherical surfaces where the electric field did not obey Coulomb's law, where it wasn't simply radially outwards from either point I or point F, or from any point in particular. The field lines would be bent in that region in order to match up the field lines outside and the field lines inside. And that region of distorted electric field is in fact part of an electromagnetic wave, because there'd be a magnetic field associated with it as well. An electromagnetic wave which would be propagated outwards forever at the speed of light, produced by the acceleration of the charge to move it from I to F. And if you had a charge sitting out here, then it would wiggle in response to the passage of that electromagnetic wave. And in other words, the wiggling would be telling us that the electric and magnetic fields are real, that it's feeling something at its location, and that it's not simply instantaneously responding to where the charge happens to be. So the fact that disturbances due to moving charges propagate away at the speed of light and things feeling those disturbances have forces exerted on them by those disturbances. Blah, blah. But anyway, that's the point. Is that's why we say the electric field is real. Electromagnetic waves can exist even in the absence of charges. And if you put a charge in its path, the charge will respond to it. So those tell us the electric field's a real thing, not just this convenient fiction that we're using to re-describe Coulomb's law. Okay, so any questions? All right, that's where we'll stop.